I'll begin. Dear Father, we thank you for staying for the break. Just pray that you'd guide our work today, Lord. In your name I pray. Amen. So I made some videos for you guys, and so on those videos I prove Cauchy's integral formula, and I indicate how we then can at least formally derive Cauchy's generalized integral formula by just differentiation. I'll start with that actually. I think it's good to see me write that out. So here's Cauchy's integral formula, which is my theorem 9.4.1, and it states this. And in view of the larger discussion, this is the m equals 0 case, all right? And so here's the fine print. Let D be a bounded domain, just merely bounded, right? A bounded domain with piecewise smooth boundary, right? And then if f of z, well, let's say if f is holomorphic with continuous f prime on D, and f and f prime extend continuously to the boundary of D, then for each z and D, we have the following formula. F of z is 1 over 2 pi I integral over the boundary of D of f of w over w minus z dw. So I worked that out in a video, which you may or may not have watched at this point, and that's okay. Watch it at some point, though, yeah? And there you will learn the secret word, if you haven't already. If you learn the secret word, do not share it with others. Make them discover it for themselves. Okay, all right. Let's see here. Now, the specific jibber-jabber in my notes, I actually have f of z is holomorphic with continuous f prime of z, right? But specifically, really think of a function or its derivative as the things which are continuous, right? F of z and f prime of z, to be, a little bit more pedantic, those are values of the function and its derivative. So it's not technically proper to say that those are continuous, right? If you want to be fussy. But more to the point, actually, I think it might be more helpful to think of it even in terms of a w, actually. It's almost f of w and f prime of w that need to be continuous in the application of this theorem in some sense. But this is Cauchy's integral formula, all right? Now, I'll show you an example in just a second here. But before I do that, let's just formally differentiate formula. Okay, there we go. So what would happen if you just differentiated this formula with respect to z? What would df dz be? Well, that would be, we can pull the 1 over 2 pi I out front, right? And we'd have d dz of this integral. And the integral is not over z, it's over what? It's over w. W is the integration variable here, right? And so there are certain, this is one of the theorems you can prove in analysis, is that given certain conditions on the thing which you're integrating, all right, you can actually switch the order of differentiation and integration. You need the function to be well behaved in a certain way for this to make sense. But again, that's really more of a discussion for a just straight real analysis class. This theorem I'm using is not a complex theorem, it's a larger theorem of real analysis. If we have a certain uniformness to the continuity of the function which you're integrating, you can swap the bounds. And you can swap the integration and the differentiation, so I'll do that here. All right. And once you do that, then you look at what you got. Well, you got d dz of f of w over w minus z, right? dw. What happens? Well, f of w is just a constant with respect to the z differentiation, right? So we can pull that out. And you're just looking at the derivative of the reciprocal function, which is what? So we've got integral, you got an f of w, right? And then you're going to have minus 1 over w minus z quantity squared, right? Chain rule, d dz of what? W minus z dw, yeah? But what's d dz of w minus z? So you guys tell me, what's the derivative? Right, minus 1. So that minus compensates with the minus from the derivative of the reciprocal function to give us a net positive, right? And so there you go. That's the formula, m equals 1 formula. We have that f prime of z is 1 over 2 pi I integral of the boundary f of w over w minus z quantity squared dw. Now differentiate again. And what do we get? This time, using the same trick, we get 1 over 2 pi I. The differentiation of the minus 2 brings out a 2 up top, yeah? Integral over the boundary of d, f of w over w minus z, this time cubed, right? Again, differentiate again. We get the third derivative at z is what? Now we get a 3 times a 2 over 2 pi I integral over the boundary of d, f of w dw over w minus z quantity to the 4th power. A pattern starts to emerge here, right? You start to see every time we differentiate, we pull down another copy of the power in the numerator. The minuses always cancel out from the chain rule. And there's a pretty clear pattern emerging. And so here's the pattern. This is the generalized Cauchy. I usually put Cauchy first, don't I? Cauchy's generalized integral formula. So it comes with the same strings attached. The same strings are attached as in the theorem I wrote at the start of class. We still are assuming what? F and its derivative f prime are continuous on D, right, which is a bounded domain. And also they extend continuously to the boundary. I'll draw a picture to explain what that means in a second here. But anyway, you see the pattern emerging. We have that the, let's say, if we want to say the mth derivative at z, well, that's going to be equal to, apparently, m factorial, right, divided by 2 pi I times the integral over the boundary of d of f of w dw over, what is it, w minus z. Not to the m, notice, it's always to the m plus 1. So this is Cauchy's generalized integral formula. Now, both of these that I'll box here shortly, it's often convenient to take what's given here and kind of repackage it. All right, so we can repackage these by solving for the integral at play, and that gives us a computational device for just straight calculating kind of interesting complex integrals. So if we solve this for the integral, what do we got? Integral of f of w dw over w minus z on the boundary d. What's that equal to? Well, it's equal to, apparently, 2 pi I f of z, yeah? So you could look at it like that. This one, we could trade for, you know, integral over the boundary of d of f of w dw over w minus z to the m plus 1 equals 2 pi I, the mth derivative evaluated at z divided by m factorial. And then finally, yet one more rewrite, which I encourage you to keep on your shelf of things to look at, which is sometimes useful to just rewrite the integration variable as z instead of w, because oftentimes we face integrals which have z as their integration variable, right? So just to avoid the amount of operator overloading in your head, think about it this way. Integral over the boundary of d of f of z dz over z minus z naught to the m plus 1 is equal to 2 pi I, the mth derivative evaluated at z naught divided by m factorial. I often find that the exploding formula here there, now it's exploding. That formula is often useful at this stage in the course anyway. So any questions before I go on? Yeah.
What is f of w?
F of w is whatever function we're integrating. I mean, it's a function which is holomorphic with continuous derivative on d. It could be anything.
But it's different from z. Like, are they related?
Are z and w related? No. Z is a fixed point. So here's the picture. This theorem. Z is a fixed point in the domain. So the domain could be something crazy. It could have holes. It could be like Swiss cheese, you know? It could just be everything except for, that could be D, right? Z is a specific point in here somewhere, all right? So Z is a fixed point in the domain, which you then apply the theorem to. W is not a fixed thing, it's an integration variable. So W is varying over the boundary of D. And the boundary of D here is rather complicated, right? There's the outside counterclockwise, the inside clockwise, yeah? These would be clockwise, each one, right? Now, I stated that f and f prime extend continuously to the boundary of D. What that means is that you could find a slightly larger open set, right, which I will illustrate in pink. So you could find like this one does not have long to live, but you know, like expand out here a little bit, right? There's some open set, let's say D I don't know, let's call this thing D tilde, right? And so D tilde does what? So D tilde has D as a subset, right? And this is open. I guess that's not I don't, D tilde contains the boundary of D, right? So it's definitely not going to be strictly equal to it because we said D is a domain, which means it's open and connected, right? You throw in the boundary of the domain, short of some topological exception I'm not thinking of at the moment, generally D tilde is going to be a bigger set. But anyway, that's the terms and conditions. We have to have a function which it and its derivative can extend continuously to the slightly larger set. Yeah.
So you're saying D tilde is strictly larger than D union boundary of D?
I think so. Yeah.
We just have like D tilde equal to D union the boundary of D, and we're not saying it's holomorphic on that because it's not in the domain. We're just saying that it's.
Well, that's what it means to extend continuously. I mean, I want a slightly larger open set actually. Yeah.
So you couldn't just extend it continuously to a closed.
I don't have the technology for that in here at the moment. I mean, maybe that's possible in a larger discussion of topological constructions, but okay, so pragmatically, let me try to cut through the noise here a little bit. Like how do we apply this theorem? Is you face an integral, right? And so here's an example. What if I was to say integrate, I don't know, dz over z minus 2, and let's suppose that the curve we're looking at is, I don't know, unit circle, right? Counterclockwise oriented. what would the answer be? This function, right? What is this? Where is that troubling? It's got trouble over here, right? Z equals to 2 gives me a divergence, right? If you think about plugging in z from the unit circle into z minus 2, we don't get division by 0, do we? Can you tell me a primitive? I mean, can you tell me an antiderivative for 1 over z minus 2 for the unit circle? Log of z minus 2. Which log? I mean, maybe.
Log sub pi.
Log sub what?
Log sub pi.
Log sub pi.
Subtracting 2, then
I mean, is this, my question is the derivative of the log, let's start out with the principal log and see if that makes sense. I mean, this is 1 over z minus 2 for what? Where is that calculation legitimate? What do we need? We need that z minus 2 is not an element of what? I mean, or more positively, z minus 2 is an element of what? The slit complex plane, right? That's what the domain of the principal logarithm is given to be in terms of, well, the domain on which the principal logarithm is holomorphic, at least. Okay? So is z minus 2 in the slit complex plane if I'm pulling z from this unit circle? For all except 2 points.
So if we use the other slit, the C plus.
Wait, so you're saying z equals to 1 and z equals to minus 1 are troublemakers? Yeah. So that's not going to work for us. We don't want trouble points. So that logarithm, how about, what if we used, oh man.
Or sorry, log sub 0.
Log sub 0? Will that work for us? Then we need that these are in C plus, right? We lose the positive axis. Yeah, I think we're going to be okay, right? Because the trouble with C plus, right? It's what's it missing? Sorry, I mean I'm having some kind of trouble with my thinking. This is not that complicated.
If you let
That's
f
fine.
of z equals z minus 2, and then you do f of the unit circle, and you draw a picture of that, it makes it easier to see.
Say again? What do you want me to do?
So you take the unit circle t, or whatever you want to call it, and you do f of that, where f is f of z is z minus 2.
Mm-hmm.
Draw a picture of it, and then you'll see that it doesn't intersect with the positive real axis.
So what you're saying is I should just translate this 2 units to the right or left?
Left.
Left.
Because it's z minus 2. So f of pi minus the circle.
So what am I drawing a picture of here? This is z minus, these are the points.
That you're feeding into volume.
This is z minus 2 for z and c. Yeah, that is the thing we want to think about. That's what we're trying to think about, is what are the inputs that we're potentially putting into a log. So if we do think about that, we've shifted the circle over there, right, which is why the log sub naught works just fine, right? And so in other words, this is equal to the integral of the differential of this, right? Which is just 0. So this is an example of where I do not need Cauchy's generalized integral formula is actually my point. All right. So there's already a class of problems we can work without Cauchy's generalized integral formula. These kind of problems have the feature that the function which we're integrating is holomorphic around the curve, that you can actually find a potential that goes all the way around the curve. Now, you see, it's not enough for okay, so getting to the point here. What would happen if we shifted the, if we say instead integrate dz over z minus 2 around the, let's say, circle z minus 2 equals to 1 counterclockwise, yeah? Then there's nothing, there's no amount of cleverness on my part. My choice of logarithm isn't going to help us. There's a division by 0 at the center of the circle on which we're integrating, right? And no amount of clever choice of which logarithm I'm using is going to fix that, right? The point is there's a divergence for the complex integrand inside the region which the curve which we're looking at bounds. So that's the kind of problem where Cauchy's integral formula or generalized integral formula is especially useful. So here, what you have to do is we have to identify what we're looking at. So this is really f of, so let's say f of z is equal to 1 over z minus 2. I'm using the exploding formula. And what's my z naught? Oh, sorry. Well, yeah, it's fine. I guess in my current vernacular, z naught's equal to 0, isn't it? Yeah, that's not what I want. I'm not saying this right. Let's try that again. What's f of, I'm an idiot. What's f of z here? F of z is 1, right? You're right. What's z naught equal to? 2. Sorry, I hate it when I have a meeting before this class. It corrupts my teaching fundamentally. It really does. Okay, so with that identification made, is the function holomorphic with continuous derivative? Yeah. So definitely we can apply Cauchy's integral formula. What's Cauchy's integral formula say? M equals 0, right? And so what we got? We got 2 pi I, the 0th derivative, right? In other words, f of 2 divided by 0 factorial. Or, of course, you could go back to the blue formula, right? If you want to, you can go back to the blue formula over there and just use that directly. The point is the generalized integral formula collapses back to that blue formula because 0 factorial is 1, and f of 2 is, well, anyway, the answer here is 2 pi I. Now, could you have calculated that directly? Yeah. You could have calculated that directly much faster at this point, right? But let's look at another example. What if we were going to, say, integrate over that same circle, z minus 2 equal to 2, counterclockwise oriented. And suppose we had, I don't know, sine cubed of z squared plus 7 e to the z divided by, I don't know, z minus 2. right? Well, guess what? The function f of z equal to the cubed sine of z squared plus 7 times e to the z, this is still, holomorphic on d, which would be, z such that what? Z minus 2 less than or equal to 2. So on that disk, the disk of radius, did I say 2? Why did I say 2? I meant 1. I'm an idiot. 1. I mean, you could do it for 2, but I was trying to make it the same as the last example, yeah? So the disk of radius 1, if you look at that disk, is the function sine cubed z squared plus 7 times e to the z holomorphic. In other words, can you take a complex derivative of it without, yeah, that's just a sine cubed and it's an exponential. These are both entire functions, and z squared plus 7 is entire, right? We have the composite and product of entire functions, which is once more entire. In fact, this function can be complex differentiated for any z in the whole complex plane. So as you look at this integrand, the troublemaker is solely the z minus 2. And that makes this a problem for the Cauchy's integral formula. All we have to do is go, okay, well, Cauchy's integral formula applies. This is 2 pi I times f of 2. So the answer is 2 pi I, sine cubed of 11 times e to the 2. There you go. That, yeah. Now do that calculation directly. Good luck to you. Yeah.
What happens if we try to apply Cauchy's integral formula to the original example we were trying where we got 0?
Aha. Let's see here. We should be able to reproduce that 0, right? So, but we can't. And the reason we can't apply Cauchy's integral formula to the original problem, it's very simple. It's because the point z equals to 2 is outside the d on which we would, so what's d here? C is the boundary of d that we might apply it to. Maybe that's the thing I've been neglecting here at this discussion, is that we're looking at the circle of radius 1 centered at 2, yeah? So the d is this shaded in thing, right? And d is that whole thing. The boundary of d is the curve which is given, this thing, yeah? And the reason that it makes sense to apply Cauchy's integral formula to this example, but not the first one, is because 2 is a point inside d, whereas up here 2 is not inside what you would probably want to make d.
But we could define D to be the region outside, it's just it wouldn't be bounded.
Yeah, if we apply it to be the region outside, then that would not be bounded, which would mean that we would need another set of tools to work on such problems. And I'm not saying such tools don't exist, but clearly there must be other bells and whistles attached to that, yeah. Okay, so what would happen? You see this problem? We could do this same problem, but with z minus 2 squared into the denominator. What would it change? If I was integrating this same thing, but with z minus 2 squared, what's that look like? So if I put, integral of sine cubed z squared plus 7 e to the z over z minus 2 quantity squared, then what I have to do is I get 2 pi I, and so I'm following this, so I get 2 pi I over m factorial. Here m is equal to 1 in this case, right? So I'm dividing by 1 factorial, which is not especially interesting. And then I'm supposed to take d dz, yeah, and evaluate it at z equals to 2, and I got to differentiate this thing, yeah. Now it's not quite as much of a snooze fest as the past one, right? But differentiating isn't that big a deal, right? Like you can do that. That's 2 pi I. Oh, 3, 3 sine squared. Why am I actually doing this? 3 sine squared. Yeah, actually, you guys can differentiate it and plug in 2, right? Everyone here can differentiate that and plug in 2. You know what I'm saying? I don't need to actually do that calculation and waste precious class time on that, right? Right. You would be better served by me working a less obvious problem. See, because some problems, like the example of the notes, don't come. I mean, these are just kind of in-your-face Cauchy's generalized integral formula problems, right? Because there's a z minus something sitting in the denominator, and the something where it's divergent is within the curve, which is of interest. So you can view the curve as the boundary of a region, a bounded region that fits the terms and conditions of the theorem. What, sometimes can be a little bit sneakier is if you got something like, I don't know, let's see here if I can come up with one. E to the z divided by z squared plus I. There we go. That's kind of interesting. But that's too interesting. Let's make it less interesting. Maybe it's not. So my question, and we're going to add the circle here, the curve which we're interested in momentarily. Let's figure out where the denominator is misbehaving. Where is z squared plus I divergent? So, fun fact, you guys. This could have been a homework problem, but it just didn't happen for you guys this semester. But oftentimes, one of the things I'll ask you to prove in complex analysis is that the quadratic formula actually makes sense if you technically read the formula as it ought to be read. In other words, that the square root is in fact interpreted as the principal square root. That makes sense, actually. So this would say that z squared is equal to minus I, yeah? Which would say that z is an element of the, the half roots of minus I. But the cool thing is, when you look at 1/2 roots, what's the principal second root of unity? It's e to the 2 pi I over 2, which is e to the pi I, which is minus 1. So this is in fact nothing more than, the square root of minus I, the principal square root, and minus that. Which is to say that you can actually go from there to this without thinking. Don't tell Dr. Scambortis. Square root of minus I, that will not make him happy. You should think hard when you make that arrow. That would make Dr. Scambortis happy. This is one of his pet peeves about students who do not think about going from there to there properly. Anyway, so there it is. Those are the roots of z squared plus I equal to 0. Now to actually calculate that, that's plus or minus the square root of what? What's minus I? That's actually e to the minus pi I over 2, right? And e to the minus pi over 2, so you got plus or minus e to the minus pi I over 4 is actually what you got there. I can draw those. So we're looking at trouble spots about here, and wait a minute, minus pi I over 2, so that's down here, isn't it? Here, and then where's up here, right? So these are your two troublemakers. That's plus or minus the square root of minus I, right? Those are the places that the denominator would be 0. So we can actually, I guess it's even before Cauchy's generalized integral formula, we have a more basic theorem, which was what? Cauchy's theorem, right? What did I call it in here? I'm fuzzy, but that stated that if we integrate a holomorphic function, right, around a bounded domain, what's it work out to? We use Green's theorem, we use Cauchy-Riemann equations, I derived it in class. Work 0, right. So if I was to take a curve like this, right? And then if I took a curve like this, then on the inside of that, the function in question, right, is holomorphic. And it extends continuously to the boundary of that. So I already know if I were to look at the boundary of the blue hatched region and calculate the integral of that over that, it's 0. Because this function is holomorphic on that set. The divergent points are outside the set, so it integrates around that, the boundary of that to 0. What's more interesting is if we enclose one of these divergences, then the Cauchy's integral formula is how we calculate. So if I was to say, I don't know, what's your favorite? See, the thing is, you can take anything you want. I don't care, whatever it is. Something like that, let that be C, right? So here's my C, which is the boundary of some region D. And on this D, right, if that's my D, you see this is really what? We got to think, we got to use our imagination. And you got to see this for what it is, which is, this is e to the z over, let's see, which one, this one's what? Z naught equals to what? Minus e to the minus pi I over 4, right? In other words, this point up here is minus the square root of minus I, yeah? It's that 0. So, all right. So z minus the square root of minus I. That function is fine inside D. The function I just wrote there, this guy, has no trouble in this region. No trouble at all. Right? Because the place where the pink boxed formula blows up is at z equals to the square root of minus I, which is the point which I'm about to circle in green down here, right? This is trouble for this guy. But that's outside the pink region, right? So, but on the other hand, this actually factors into what? Z minus the square root of I times z plus the square root of minus I, right? So I have to think about the thing boxed in pink as my f of z, right? This is the f of z for the theorem. And down here is your z minus z naught. So we get 2 pi I f of, what was my z naught? Minus the square root of minus I. By Cauchy's integral formula. And then I just have to plug that in. So I get, 2 pi I e to the minus the square root of minus I divided by, looks like minus 2 times the square root of minus I. And that's the value of the integral. So I told you guys last class that what we were about to start doing, you would not be able to mistake for a theorem of real calculus. I think I have made that case today. What we're doing is genuinely different than calculus 3 on steroids, right? I mean, this is something really, really new, right? And one of the points I make is that Cauchy's generalized integral formula says something really, really interesting. It essentially says that if you have a first complex derivative, you can calculate the mth complex derivative. In other words, if you have a once continuously complex differentiable function, you have a complex smooth function. There is no such theorem for real functions. Real functions can be once differentiable, but not twice. Or 3 times differentiable, but not 4 times. There's all kinds of possibilities there. So there's something genuinely special about complex analysis that differs from real analysis in this sense. All right. So that's, I just wanted to give you guys some actual examples. I hope I've done that today. The bit of theory I need to cover with you in the time that remains, it's just really a simple consequence of what we're doing, which is Lioville's theorem. And I think I'm going to use the projector actually for that. So just to give you a thumbnail sketch of what we're about to do, Lioville's theorem just takes the Cauchy's generalized integral formula and applies the ML theorem basically to it to get an estimate. And so it gives us an estimate which is very interesting and useful. If I can't, come on, come to life. And it's probably, hello. Come on, where'd you, there you are. Did you resume? I can fix, here I'll fix it. It's fine. You guys are not responsible for, that's my job. There you go. Okay, so this is this Lioville's theorem, and it basically starts by assuming we've got a function, all right, it's holomorphic on D, and you know, it is an open set D tilde containing D. F is holomorphic on that larger open set. Likewise, the derivative exists and is continuous for some disk, in the sense that it's continuous on any open subdisk of that. Given these terms and conditions, I'll find my laser here eventually. We have, of course, Cauchy's integral formula, right? For any z, we can, well, any z naught, we have this lovely result that the mth derivative at z naught is m factorial over 2 pi I. And this is not quite right. This is supposed to be equality here, right? We don't do integrals. The complex integral is an integral over a curve, not an area. So this would be a disk. We just want equality there, okay? So if we, and you can see I talk about the circle down here, right? Parameterize this circle. I should have equality there by z equals z naught plus rho e to the I theta. Then we get dz is that, you know, plug that in, what happens? You got your m factorial, 2 pi, you end up with a rho to the, come on, I need to replace the battery in this thing. Shake loose some ions. All right, there we go. So rho to the m plus 1, and then there's a rho up here, it cancels the m plus 1, just leaves me with m. And then, of course, you've got your f evaluated the parameterization. And let's see here. We've got 1 e to the I theta up here, but we've got m plus 1 of them down here. So we have a net of m in the denominator, which gives me e to the minus I m theta. Now, if we have a bound, all right, if we could bound out, suppose we have a bound for the function, which seems reasonable to do because it's a continuous function, and this is a finite, a bounded domain. So the extreme value theorem says, hey, you can bound such functions. And so here's a bound. Suppose I had a bound. The modulus of f is at most m. Then I can use the ML theorem to replace this with that. And again, I'm assuming that that is less. I'm assuming that, I guess I got to use point. This right here is at most m. And then you're integrating d theta from 0 to 2 pi. Well, that gives us 2 pi m. All right. All right, so, oops, hey, but, come on. And so that brings us, that essentially, because all you got to do is, stupid, this is the worst. This is stupid argument straddling a page. All I'm doing is I'm taking the bound, if you bound this thing, right? I've just showed that when you actually do the calculation of this, the modulus of this is at most what? Oh, I do have the, so I just showed that I had the m factorial, didn't I? M factorial over 2 pi I. This, did I keep that down here? No, I'm just working on that piece, right? So what I've showed is that the modulus of this part is at most 2 pi m, right? I still got the m factorial over 2 pi, rho to the m there. So, great. that brings us then to divided by rho to the m is a bound for the mth derivative at z naught. So that's just coming from, that rho to the m was in the estimate we just found. The 2 pi's are canceling. There's the 2 pi I in Cauchy generalized integral formula. There's the 2 pi from the integration we just did. Yeah, those 2 pi's cancel. The modulus of I is just 1, so that goes away in the calculation. But this is really just a straightforward calculation from Cauchy's generalized integral formula. This bound pops out. We have that the mth derivative at z naught is bounded by m, where that's a bound for f itself, m factorial divided by rho to the m. And that gives us Lioville's theorem, among other things, which says this. If f is holomorphic with continuous derivative on c, and if you have that function's bounded, all right, if a function's bounded on the complex plane, then that implies it's constant. That is a very interesting result. So the proof is absolutely simple. If we have f as continuous and bounded on all of c, then we can consider the disk of radius r naught, r centered at z naught, use Cauchy's estimate, all right, with m equals to 1, so that gives us m over r. What happens as r goes to infinity? See, as r goes to infinity, this goes to 0, which says that the absolute value of the derivative at z naught is 0. But both r and z naught are arbitrary. So this shows that given any arbitrary point in the plane, there's a disk of radius r on which the derivative of the function is 0. That's to say that the derivative of the function is everywhere 0, which is to say that the function's constant because the complex plane itself is connected. And that's Lioville's theorem. Now, so this, now I gave you guys a homework problem where you essentially get to prove the fundamental theorem of algebra. And I don't think it was this proof that I'm talking about here. But I'd say, well, I'll try to come back and think about this after you guys have done your homework. So like problems 49 and 50, if I remember right, the ones I just created, are related to this, but maybe they're not exactly the same. I'm not sure. But anyway, that's pretty much it for chapter 9. So we will move on, I think. I need to look back at my schedule, make sure I'm not missing something, but I think that's it for here. So thanks, guys. I hope you had a good break. Yeah. I will shut up. Ready to get it? Oh, no.